this chapter we will be studying the transformations of functions. In this lesson we were going to be looking at translations of functions. But we begin by first looking at what we will call basic functions.
So before we get into the actual point of this lesson, we want to introduce this idea of transformations on functions first. Okay, this is really your first step when you talk about transformations. This is really your first step, a much larger idea in mathematics. Okay, but an incredibly useful idea. However, I want you to be aware that as you progress through this chapter, the ideas are very, very simple. Okay, they are very, very simple. But you do get to a point where it can get quite confusing, and I'm going to just throw that out there right now. Okay, there will be a part here where, for example, you're going to wonder, like, is the number supposed to be 2 or is it a half? Am I going to the right? Am I going to the left? And there's some decisions that you got to make here. I'm going to try really hard to make it clear for you as you go through this, so when you get to those points, that decision isn't that hard for you to make. But I do know I've witnessed a lot of students struggle with this. Now, let's talk about what a transformation is. Okay, a transformation is a change that you make to a graph of a relation, okay, or a function or whatever. But what we're doing here is we're going to keep the same overall structure of a function or a relation, but what we're going to do is we're just going to change, for example, its position, okay? We might translate it, which means we're going to move the object around. It's going to maintain its shape, but it's going to be moved, okay? And you can do that left, right, or up and down. We can stretch this thing, okay? We can kind of like stretch it out vertically, stretch it out horizontally. We can even do more than that, but those are where we're going to focus on in this chapter. Which again, it does change the shape of the object, but the general structure, like a quadratic remains a quadratic. You wouldn't stretch a quadratic into a cubic or something like that. Okay, so it remains quadratic, but we're changing the shape here. We can reflect it, which means we're going to change its orientation on the graph here. But again, if we're talking about, for example, a radical function, a square root function, or even the rational function, it continues to be rational or radical or whatever, but it's just its orientation on the grid or the Cartesian plane changes. Now, before we get too far into this, we want to make sure that we've gone over the comparison between set notation and interval notation again. And I know we've talked about this, but just to reiterate it, if you've got this interval between a and b, where a is less than x is less than b, okay, here's your set notation, and this is the one that we're probably mostly familiar with here. This is the one that gets a little bit confusing, okay, because we start to use parentheses when we are not including the endpoints. Now, I know again that looks like a point, but it's not a point. This has to do with context. You would know in context that this isn't a point. This must be referring to the interval between a and b. Okay, so they're not included when you're doing parentheses. However, when you use the square brackets here, that implies the or equal to. And so in this case, we are including those endpoints. Now, again, before we get into the real meat and potatoes of this particular chapter here, what we want to do here is we want to go through and review some of our more basic functions here and make sure that you understand what these things look like. Okay. Now, the reason for that, whoops, I'll zoom out just a little bit here. The reason for that is because we're going to start to transform these objects, but their basic structure stays the same when we do that. So I want you to know when we start translating, for example, a linear function, what exactly the original basic linear function looks like. Now, we've chosen to throw this at you here. I'm gonna adjust this just a little bit here. This one has already had a couple transformations in it, but we throw this at you because you should know what those are. This right here means there's been a y-intercept of -3, and it's got a slope of 2, so up 2 over 1, and then we can connect those dots there. It looks like that. Okay. The domain is going to be all reals. The range is going to be all reals. Now, that's great. That's what that one is. The more basic linear function, though, is simply y equals x. And we saw this. This is going to become important here. Y equals x is just this line right here. It's got a y-intercept of 0, okay, and a slope of 1. But again, its domain and range are all reals, all reals. Okay, this is the more basic one. This is the one kind of I want you to think about here. But you should know what those pieces are doing anyway. okay? So this right here has already been transformed. This is a transformed version of this, and we'll talk about what those pieces there are doing in just a little bit here. Now let's move on and take a quick look at the quadratic. Okay, you spend all of Math 20 basically looking at this. So the quadratic is just going to be the parabola. Okay, it's going to look like that. The domain will be all reals because you can square basically anything. The range, however, is going to be greater than or equal to 0, okay? Remember that the result of squaring is always going to be positive, or 0 if you square 0, okay? So you just need to know that. The cubic, okay? The cubic looks like this. It kind of comes up, it levels out, goes through the origin, and then when it passes through, it curves up like this, okay? Its domain is all reals because you can cube anything, and because cubing a negative leaves it as a negative, what will happen here is you will get the range being all reals as well. Now let's move on and take a quick look at the square root function, our radical function, if you will. The graph of this thing looks like this. It starts right here on the origin. The square root of 0 is 0, but it goes this way. Okay. The square root here, when you take the square root of a number, you can only take the square root of a positive number or 0 and get a real result. But the result will be positive. That's why it extends up into that first quadrant there. My domain here will be that x is greater than or equal to 0, and the range is that y will be greater than or equal to 0. Don't forget the or equal to 0 here, okay? A lot of times people, because we know that there's a limitation on the domain of the radical here, we know that you can't take the square root of negatives. People tend to lump the 0 in that, but you can. You can take the square root of 0. Okay? The absolute value function. Here's something, again, that you should recognize from Math 20. Well, I probably could have drawn that better, but that's what this thing looks like here. Just the basic absolute value function has that very stereotypical V shape to it. Once again, you can take the absolute value of basically everything. And the reason that's true is because by definition the absolute value is the distance that a number is from the origin. So basically I can compare any number along that number line to the origin. That's easy. The range, the results, will be greater than or equal to 0 because I do hit the origin right there. Okay, 2 to the x is my exponential function. Now the base can change, and you're going to study that a little bit later on in this course. But the 2 to the x is really about the simplest you can get here. You certainly don't want to put a 1 in there. 1 as a base is incredibly boring. 2 at least starts to show you some of that interesting behavior here. Okay. Now my domain will be all reals. Okay. This thing will extend infinitely to the left, infinitely to the right, but it shoots up really, really fast once it crosses the y-axis here. The range, in this case right here, you do not include 0. There is no exponent you can take to 2 that will create a 0. There is nothing here that will make this equal to 0. Okay, that's an interesting thing to note, kind of store away in the back of your mind, because that's going to come up later on in this course. And then finally, this one down here, our rational function, y equals 1 over x. This is an interesting one. Okay, the result, okay, when you graph this, and you can verify this in your calculator, it's going to look like this. Okay, and it's going to come over here, it's going to look something like this. That's not the best rational function, but that's what it looks like here roughly. This is called a hyperbola. Now, unfortunately, we don't spend a lot of time studying that shape, but we will be transforming it. The domain here, well, 0 is a non-permissible value here, so the easiest way to describe this is to say that x cannot equal 0. Whoops, can't see that. X can't equal 0. Now, it turns out the range basically kind of suffers the same problem here. No matter what value you plug in for x here, there's no way to make this ratio equal to 0. So that means that as a result, the y will never equal 0. It can equal anything else, just not 0. And so those are some of the basic properties of the basic functions that we are going to start transforming here.
We will now take a few moments to review function notation.
Now, another thing that we need to review here before we can jump into the first real lesson here, we got to review function notation. It's very interesting to me that that people struggle with this. Because we go over it in grade 10, you introduce it in grade 10, I should say. We go over it in math 20, and then we're using it again in math 30 here. But you know what? And you can kind of survive this course with kind of a limited understanding of function notation, but once you get to calculus, it really becomes apparent whether or not you've really understood what this means here. I want to talk about this really, really quickly again. So in function notation, y is replaced with f of x. Now, I really want you to think about that. Don't think of it so much as y and f of x. These both represent what we call the dependent variable, okay? These are dependent variables, the y and we say it down here how you read it. You read it as f at x or f of x, but that whole thing there is your dependent variable. That is what you put on the y-axis here, okay? So now the equation 3x plus 2 is rewritten as f of x equals 3x plus 2. Now I want to talk about what we mean by that. So when we talk about 3x plus 2, granted, when we plug the f of x in there, that's replacing the y with this larger symbol, and in many ways it doesn't look like it's much of an improvement here. And yes, we are using f because it's called a function, and that's a way of labeling it here. But I want to talk about what the f represents. The f in this particular case represents multiply the independent variable. Now I'm just going to use, just independent variable by 3 and add 2. Then what you put in the brackets here, okay, what you put in the parentheses, that is, yoink, the independent variable. Okay, so whatever shows up in between those parentheses, that is the independent variable. So then multiply the independent variable by 3 and add 2. F of x means 3 times x plus 2. Okay, now the reason why I go through a lot of trouble here just to explain that, to make you understand what the f stands for. The f refers to the functional rule being represented here. Then the parentheses tell you, okay, that parentheses right there tell you what the independent variable is. Because there's some notation that's going to come up later. And if you don't understand function notation, some of the notation that we use in a little while here doesn't make any sense. But if you understand what the parts represent here, then the notation makes sense. And math is notation driven. Okay? When there's weak notation, you can't do much with math. Okay? So anyway, let's move on here. So again, another one of the strengths here, or at least a benefit here, is we want to understand that a coordinate, the coordinates of a point here, x comma y, really should be understood as x comma f of x. Okay? And here, you really get a wonderful sense of this. This is the independent variable. And when you think of it as f of x, as a function of x, then you really get a great sense of how this thing depends on this one. Why we call it the dependent variable. Okay? So down here, very, very simply, and it's written like this basically just to move us on into the lesson here, but f of x does not mean f times x, okay? Rather, it's the name of the function. What f means is it's the rule. I'll just say it again. F represents the rule. That has to be defined, okay, before you can do any calculations with it, but it represents the rule, and what's in parentheses represents the independent variable.
If f of x is equal to x squared plus 4x plus 3, find the following in simplest form.
Okay, so in this case right here, notice again that f of x is x squared plus 4x plus 3. So what we're saying here, what f is square the independent variable, add 4 times the independent variable, add 3. In this case, the independent variable is x. Now let's move down to here. Here, what's inside is the independent variable. So my rule f says take the independent variable, what's inside, square it, add 4 times the independent variable, add 3. So 9 plus 12 plus 3, well 9 and 3 is 12, 12 and 12 is 24. Okay, so there's our first answer here. Now, take a look over here. 3 times f of x, okay? 3 times the function. Now, there's later on in this chapter, oddly enough, this becomes a big stumbling block for people. This is 3 times the function, okay, the entire function. Now, the mistake that a lot of people are going to make here is they're going to say, well, my function here is x squared plus 4x plus 3. So what they're going to do is they're just going to put 3 in front of the x squared plus 4x plus 3. Well, the 3 is right here, and this is f of x. But that's wrong. Okay, that's very wrong. Okay, this is 3 times the function. So what is the function here? Well, this entire thing is the function. 3 is multiplied by the entire function, which means it must be distributed to all the terms in that function. So 3x squared plus 12x plus 9. You must understand that if you're going to understand what's going on in a couple lessons down the road here, okay? So that's really important. Can't overstress that enough. This will become a big issue for people who are going to assume that this behaves differently than it does. Down here, f of 3x, okay? And again, people make weird assumptions about this. Now remember what my function does. I'm going to slide this down here. Okay, the function is square the independent variable, add 4 times the independent variable plus 3. Whatever's inside the parentheses is the independent variable. So in this case, 3x right here, this is taking the place of my independent variable. So my function says square the independent variable, add 4 times, whoops, sorry, I don't want to throw you off here. 4 times the independent variable plus 3. Now I have to do that. Now 3x squared becomes 9x squared. 4 times 3x is 12x plus 3. And so that's what that becomes when I reduce that. Over here, f of x plus 3, notice that this is happening, okay, kind of outside the function here. This is happening after the function's been dealt with here. So again, I'm going to represent that f of x in parentheses here. So x squared plus 4x plus 3, okay, because this is simply telling me square the x, add 4 times the x plus 3, and then I'm going to add a 3 out at the end here. And when I simplify that, it looks like that. Okay, so there you go.
If f of x is equal to x cubed, write the following in terms of the function f.
So I love this question. I think this is wonderful. The idea of kind of getting you to go backwards with the function notation. I think if you can walk this one through here, you should really get a sense of what's going on here. The function that I'm working with here is f of x is equal to x cubed. Okay? Now, look at what's going on here. X is being cubed. Well, that's f of x. This is f of x. So where does that 1 fit? Well, that's outside. So this is simply going to be f of x plus 1. Remember, f of x, in this case, is x cubed. Over here, notice what's being cubed. It's the x plus 1. Well, okay, let's go back to my original function. What does the f mean in this case right here? Well, what it means is take the independent variable and cube it. Okay, take the independent variable, whatever's inside the parentheses, and cube it. So over here, what's being cubed? X plus 1. So that has to be the independent variable. So that has to go inside the parentheses there. Okay. I hope that makes sense. Down here, 5 times x cubed. Now, is the 5 being cubed here? Nope. Nope, not at all. Now, you could think of it as being cubed, but I'll have to show you how that works here in just a second. But a natural first glance of that, no, the 5 isn't being cubed. It's being multiplied after the x is cubed. And so what would happen here is I would think of this as 5 multiplied by f of x. Okay? Now, I could think of it as whatever, something being cubed to create 5. Like I could have seen this as, for example, this could have been the cube root of 5 times x cubed, which would have given me f of the cube root of 5x. However, that's awkward. That is a needlessly awkward way of interpreting that. So this is the more obvious way of doing it, okay? However, this could work here, because if you cubed everything inside here, you would get 5x cubed. But this last question does a better job of that. What is being cubed here? Well, in this case, it is the 5x. It's this, both of those factors together. So the natural way to interpret this would be, okay, that must mean that 5x in this case is taking the place of the independent variable. So if it takes the place of the independent variable here, it does so also in function notation. I hope that helps make a little bit of sense of this if you were struggling with it.
Now we will start talking specifically about horizontal and vertical translations.
So a translation, whether it be horizontal or vertical, is a transformation where just the position of the graph is changed, okay? So that's the key word right there, just the position. All we're either doing here is moving it left or right or up or down, okay? We're not changing, and as it says right here, we're not changing the size, the shape, okay? We're not like kind of deforming it, okay? Not even changing the orientation of the original graph, just the position. And so any transformation, like it says right here, any transformation can be represented using mapping, and I love it when the curriculum uses the correct vocabulary, okay? Yeah, we're talking about mapping that relates one set of points to an image, okay? To a new set of points here. Now, the way that works here is, what we're going to do here is, the way this image or this mapping works is we start with x and y, and it maps to a brand new set of points here where we do something to the x, we do something to the y, we're changing the point. Okay, we're altering the point to create a new point. Now, when we talk about just a horizontal translation, okay, that's going to move the graph either to the left or to the right here. Now, right here, and we're just going to give you the information here, it moves right if in the function here we've got x minus h, where h is positive. So just to give you a sense of what that means here is, let's say that I've got something like x squared. If I put into this y equals x minus 2 squared, okay, now notice in my notation here that this is x minus h, but I'm insisting that h is positive here. So think about this. What would my h be here? If this is x minus h, well, we know that h must be 2. And that should give you an idea of this being 2 to the right. Now, another way that might help you understand how this works here, because a lot of times when people look at this, they'll see x minus 2, and we tend to associate minus with going to the left, and we should. I mean, that's the correct assumption to make here. But in this case here, when you see a minus inside that notation, actually it means going to the right 2. Now, another way to think about it here is, what would you do to get x by itself here? If you were to isolate x in this notation, well, the very first thing you do is you take the square root, and the very last thing you do is you would add 2. You would take the square root of y, and then you would add 2 to it. That becomes your translation, adding 2 to x. That is how we create our new x coordinate, okay? So now, the different ways we can look at this is we start with the original function, and in this function, we are going to now replace the independent variable with x minus h. This becomes my new, in fact, I'll zoom in on this. This becomes my new independent variable, x minus h. So inside the function, that looks like this. But how does that affect the actual graph? This is the function. How does it affect the graph? Well, my point, x comma y, is going to become x plus h comma y. Because think about it. Right here, if I was to get, over here, if I was to get x by itself, okay, I would undo the function, whatever that is, to get it down to this, and then I would add h to get my new x coordinate. And so that's what we're doing, okay? And there are two different things that you're going to see here. In the function, you're going to see x minus h, but here you're going to see x plus h in the point, okay? And when I describe the transformation, when I give the description, anytime that you give the description of a transformation, you're describing what you're seeing in the point, not what you're seeing in the function, but what you're actually seeing on the graph. Like, this is the thing that you're graphing. This is the visual part of it, okay? Now, if we've got this x plus h showing up in the function, that's because h is negative. Now, let me explain that. Let's go back to my x squared example here. So we start with y equals x squared. If I now see inside here, let's say x plus 3 squared, the better way to think about it is this was x minus negative 3. Okay, because we want to go back to our original expression here, f of x minus h. This is the standard way to write that. So that subtraction changes to a positive here if the h is negative. So x minus negative 3 becomes x plus 3. Now, I want to ask you here, what would the last thing be that you would do to get x by itself? Well, I would square root the y, yeah, and then I would subtract 3. Okay, that becomes my transformation, 3 to the left. Okay, so let's take a quick look at our points here. So I've got y equals f of x. This is my original function. I am going to replace in the function, okay, because that's what we're talking about every time we talk about replacement. I mean in the function. Actually, I should have probably written that up here too. In the function, I'm going to replace my independent variable x with this as the independent variable. Okay, so in the function right here. Here's my transform function. Now, that means x minus h comma y here. And this right here means h units to the left because this is subtraction. Because remember, this describes what is actually happening on the point. This is what I'm seeing. But in the function, you're going to see x plus h. Because the only way to understand what's going on to x is to isolate it. Now, that's what's going on horizontally. Now let's take a quick look at the vertical transformation. Okay, and actually, other way. The vertical transformation is in many ways simpler. And I say that because in the last couple minutes here when we were talking about the translation on the x here, I was telling you to isolate the x, isolate the x. Well, the thing is we don't often isolate the x, but we always isolate y. And so that makes it often a little bit easier for us to understand here. So vertical translation simply moves the graph up or down. And notice that if you've got the on your function here, you put in a y minus k, normally what we'll do is we'll move this over and get the y by itself. So what do I got to do to get k to the other side? I have to add it. Okay. Now let's assume k is positive. So for example, this would be something like y minus 2 is equal to f of x. So k is positive 2 here. I bring that to the other side. I get f of x plus 2. That's what I got to do to get it to the other side. So when I see that sitting there already on the other side, I know that I've moved this thing 2 up. So the way this works here, here's my function. I'm going to replace this. This is in the function. Every time I do a replacement, it's in the function. So I'm going to replace the dependent variable with this, y minus k. So in my function, I get this, but then I immediately isolate it because that's what I do. That's what we always do. We're always solving for y, okay? And that k occurs outside the function here. So now we got something to compare to. Notice that the vertical transformation is occurring outside the function, whereas the horizontal one in both cases was inside the function. So there's a little clue. If you ever get turned around, you're wondering, well, is what I'm looking at horizontal or vertical? Vertical's outside, horizontal's inside. Now my mapping point is x comma y becomes x comma y plus k. Now this is pretty consistent. Once you've written it in this form right here, think of it this is my old y coordinate. This is the new y coordinate. This is the old y coordinate plus a k value. So in this case right here, the point really does match up with the function. And again, my description matches what I'm seeing here. Okay, anytime I describe the transformations, I'm talking about what's going on right there. And lastly, if we're going to translate this down, what we're going to see here is y plus k, or think of it this way, this is y minus negative 3. In this case, my k is negative, and I know when you look at it, you're thinking, well, wait a minute, what that would look like y plus 3 equals f of x. That looks like the k value is positive, but it's because the operation is supposed to be subtraction. It's supposed to be subtraction. I'm supposed to be subtracting something. So if you see addition there, That's because you're subtracting a negative. Okay, and you really have to be cognizant of that. Or another way of thinking about it, if that's kind of causing you mental stress here, just isolate the y, bring that over. And what do I got to do to get the 3 over? I have to subtract it. And there's where I'm going to see my 3 down. So it's always in the process of isolating that variable that you see clearly what the transformation is. So now here's my y equals f of x. There's my the replacement in the function. So I'm replacing the dependent variable with y plus k. That looks like this, but then gets transformed into this when I bring that over. And this is what I'm seeing, okay? This is my mapping. The original point becomes this point right here, okay? And there you go. So that's a fairly quick description of some major components of a transformation, okay? And with specific reference to translations here, but you've got the original function. You're going to replace one of the variables, okay, in the function, either the independent or the dependent variable with something else. It's going to give you this, and then that corresponds to a change in the actual graph.
Sketch the graphs, state the function, the equation replacement, the mapping point, and domain and range using interval notation of the following 2 functions.
So in this case right here, we're starting with y equals x squared, and this really becomes our basic function here. F of x is x squared. And we saw previous to this that x squared is just going to be that. Okay? Now, what does x squared minus 5 do? Well, okay, notice that the minus 5 is outside the function. The function here is at x squared. This is outside the function. So in other words, really, you might want to think of it like this. My new function, okay, is really f of x minus 5. Okay? I'm subtracting 5, and I know that that corresponds to a vertical translation of 5 units down, the y-coordinate being decreased by 5. So that's going to be 1, 2, 3, 4, 5. So there's my transformed function right there. My domain, because this is a vertical transformation here, notice that this is not going to affect the domain. So the domain stayed the same. Now, it really wouldn't have made much difference because it was an element of the reals. It'll always be element of the reals. The range, however, is going to be directly affected by this. So a vertical translation cannot affect the domain, but it can affect the range. And in this case, because I've dropped it 5 down, it should have been greater than or equal to 0. Now it's greater than or equal to negative 5. Now, we're supposed to write this in interval notation, and so this is going to become negative infinity to positive infinity. I can't equal infinity, so I use the parentheses. Greater than or equal to negative 5 is going to correspond to negative 5, square brackets, okay, to indicate inclusion, but then going up indefinitely, so up to positive infinity. So, and again, I can't equal infinity. My mapping here, okay, notice that nothing has happened horizontally, so the x stays the same, but my y-coordinate has been decreased by 5, okay? So when I say a vertical translation 5 down, I am describing what's going on with a point, so this means y minus 5. However, in the function, the replacement, because this question is also asking for the replacement here, the replacement that occurred was I replaced y in the function with y plus 5. Okay? Because, again, notice that the function here, the y has already been isolated. The 5 has been moved over. So I must have replaced y with y plus 5 and then subtracted it to bring it over. Okay? And that's what this question is asking us to do. In this question, the function, okay, y equals f of x, the original here is this x cubed. Okay? Notice that what's happening right here is inside the function, this x plus 5 cubed. So this is horizontal. Okay, this is definitely horizontal. And now let's think about this. What would I have to do to get x by itself? I would have to subtract, I'd have to take the cube root first, then I would subtract 5. That's subtracting 5 to the left here, okay? So this has been a horizontal translation, 5 to the left. Okay. Now, what that looks like in my function here, because this is occurring inside the function here, the way my function would look like would be this here. I would make this x plus 5, again, inside the function. Now, x cubed looks like this. We saw that earlier. 5 to the left is simply going to move this 1, 2, 3, 4, 5. So it's going to go up like that. Okay? So this right here is the transformed one. Now, the range will not be affected by a horizontal transformation. Okay, so moving it 5 to the left won't change this. This is still going to be y as an element of the reals. Now, if a horizontal translation was going to affect anything, it would affect the domain. However, in this particular case, it doesn't. And the reason it doesn't is because the domain was originally all reals as well. So shifting it left or right simply won't change that. But like I said, if it was going to change anything, it would change the domain. It won't affect the range. Now, in interval notation, as we saw before, that's just going to be negative infinity to infinity. And again, we're using the parentheses because we're not including those. My mapping. Okay, this is what we're actually seeing. Okay, and what are we seeing here? Well, we're not seeing a change in the y, so the y stays the same because we're just moving it horizontally. But when I see x plus 5 in the function, I know that I have to subtract 5 to get the x by itself. So that means in the actual point, it's actually x minus 5. That's the transformation. Now, the replacement, because again, this question is asking for the replacement. In the function here, it's the independent variable that changed. The independent variable was replaced with, the x was replaced with x plus 5. Okay? And that's what this question was entirely asking for.
For the absolute value of x function shown below, graph y plus 2 is equal to f of x minus 3 on the same grid and give the equation of the transformed function.
Okay, so the easiest thing to do with this question is just to start with giving the equation of the transformed function. Because remember, our function here is the absolute value of x here. So when you look at the function notation here, x minus 3 is taking the place of the independent variable. So we'll just write this down here. This is the same as y plus 2. This will equal the absolute value of x minus 3. And then we can do one step better here by bringing the 2 over, isolating the y like we would normally do. Now, let's talk about what this is saying here. Okay, let's talk about the mapping here first. When you've got the x minus 3 here inside the function, remember if I was to isolate the x I should say, the last thing I would do would be to add 3. So that becomes our mapping here. We're going to add 3. Here, to get the y by itself, I would have to subtract 2, so that becomes the other part of our mapping here. So this is our new point. Now, here's how the mapping works. Okay, the mapping is x plus 3, so I'm going to take the x coordinates here of each point, and I'm going to add 3 to it. So negative 5 plus 3 is negative 2, 0 plus 3 is 3, 5 plus 3 is 8. For the y coordinate, for each one of these things, I'll subtract 2. So 5 minus 2 is 3. 0 minus 3 is, I can't believe I was about to do that wrong. 0 minus 2 is going to be negative 2. And then 5 minus 2 is going to be 3 again. And now I would plot these points. Okay, so negative 2, 3, right there. 3, negative 2, 3, 1, 2, right there. And 8, 3, so 6, 7, 8, 1, 2, 3, right there. And now if we connect those dots, that's what the transform graph looks like. And notice it's the same shape because translations don't change the way the graph looks, they just change the position of it. And so there we go, 3 over, 2 down. Exactly what we were expecting.
Given the graph below, graph the transformed function y minus 1 equals f of x plus 2 on the same grid and describe the transformations that have taken place.
All right, similar to the previous question, I think the easiest thing to do here is to, instead of graphing this thing first, let's identify the transformations. So in the function here, I see y minus 1. Now what would I have to do to get the y by itself? I'd have to add 1, okay, remember, and that makes this a vertical translation of 1 up. Now inside the function, I've got my x plus 2. This is in place of the independent variable. To get x by itself, I would have to subtract 2. I'd have to bring that 2 over to the other side. And so that's a horizontal translation 2 to the left. And so our point, now remember, the image point here is exactly in line with the descriptions. Not quite exactly what you would see in the function notation, but this is exactly what we're seeing on the graph here. So 2 to the left is x minus 2. 1 up is, whoops, sorry, that ran into each other, y plus 1. So there's our mapping here. Now, really, to do that on this graph here is really just a matter of moving the points exactly like this. So for example, here's one of the endpoints. I'm going to move this thing 1 up, 2 to the left. Take this point, move it 1 up, 2 to the left. 1 up, 2 to the left. This point, 1 up, 2 to the left. And then same thing with this one, 1 up, 2 to the left. Now, because the transformations here don't change the shape, they just change the position, I'm just going to draw this thing exactly the way I saw it previously. I could have done that a little better, but anyway, there you go. So that's the graph that they're looking for.
Describe how the graphs of the following functions relate to the graph of y equals f of x.
Okay, so this first one here, we see that the change, when we compare it to y equals f of x, the change is happening within the function. Okay, so this is horizontal. And again, think about what would I have to do here to get x by itself? I'd have to add 3. So this is a horizontal translation, 3 to the right. This second one here, f of x, notice that there's nothing going on within the function. So because this is outside, this has to be vertical. Notice that the y-coordinate has already been isolated, so what did I do? I added 4. So this is a vertical translation, 4 up. In this last one right here, okay, we got a couple things going on. If I was to get y by itself here, I'd have to add 1 to both sides. So there's my vertical translation of 1 up. And then inside the function, again, this is where my horizontal translation happens. And to get x by itself here, I'd have to subtract 10. Okay, or the other way of thinking about it here is to compare that, remember, to that, the original question that we had here was this f of x minus h. Should be subtraction. Okay, should be subtracting a positive number here. So because I see addition, this must have been negative. And that would imply to the left here. Either way, this is a horizontal translation, 10 units left. And so those are the transformations that we're seeing in this particular problem.
What happens to the graph of the function y equals f of x if the following changes are made?
So this question is really similar to the one previous to it. It's just that it's asking us to take a look at this information here and relate it to the transformations, but the information that we're given is really one step ahead of the work in the previous question. So remember, when I talk about replacement, I'm talking about replacing it within the function. So I'm going to replace the x, the independent variable, with x plus 2. So this means f of x plus 2 inside the function here. Now I can identify the transformation because to get x by itself I'd have to subtract 2. And subtracting 2 means 2 to the left. So horizontal translation, 2 left. Over here, remember I'm replacing y with y minus 8 in the function here. So the dependent variable becomes this. This is my dependent variable. So y minus 8 equals f of x. And then to get the y by itself, I'd have to add 8 to both sides, and that is my vertical translation. So vertical translation, 8 up. Those are the transformations they want.
The point 2, negative 3 lies on the graph of y equals f of x. State the coordinates of the image of this point under the following transformations.
Okay, this question is really similar to one of the previous ones that we've done. It just takes us one step further by giving us a very specific point to work with. Okay, and we're going to have to state the coordinates of that point. So we'll have to identify the transformation and then apply it. So let's take a look at this first one. If I was to, okay, notice that the 8 here is being combined with the dependent variable. If I was to get the y by itself, the dependent variable by itself, I'd have to subtract 8. So this is a vertical translation, 8 down. Now, as an image point, that looks like this. Okay, remember that it's the description that influences the image point, not the function. It's the description of the transformation. So this is going to be y minus 8 right here. And now I take my point 2, negative 3. Well, nothing happened horizontally, so the x-coordinate is still 2. And then if I plug negative 3 in, negative 3 minus 8 is negative 11. So there's the new point. Okay, let's take a quick look at this second one here. We got a little bit more going on. To isolate the y here, I'd have to add 5 to both sides. So that's a vertical translation, 5 up. And then followed by, well, look what's inside the function. Remember, if it's inside the function, that's horizontal. To get x by itself, I would have to add 7. So that's a horizontal translation, 7 right. Okay, my image point is therefore going to look like this. X comma y will become, well, what does the description tell me to do? Well, I'm adding 7 to the x coordinate, and I'm adding 5 to the y coordinate. So let's take the original point that they gave us. 2 plus 7 is 9, -3 plus 5 is 2. So the transform point, or the image point of the original that we were given, is 9, 2 under this transformation. This last one here is probably the simplest one because we're giving you the image point. So I don't need to do any of that kind of translation here. I'm just going to add 2 to that, so it's going to give me 4, and I'll add 3 to that, which will give me 0. And so that's the image point that we're looking for this question.
The point -1, 8 is on the graph of y equals f of x. State the mapping notation used, the replacements, and the corresponding point on the graph of y plus 9 equals f of x plus 4.
Okay, well, there's a lot going on in this question. I'm getting asked for a lot here. First of all, I think the thing to do here is to look at the replacements. And what we're going to do is we're going to compare kind of your original function here to the one that we are given, the transformed one here. Now, once you kind of write those together, I think the replacements are actually pretty easy to see. Notice that the y was replaced with y plus 9, and the x was replaced with x plus 4. Okay, now what does this mean here? Well, to get the y by itself, I'd have to subtract 9, so this is a vertical translation, 9 down. And to get the x by itself, I'd have to subtract 4, so that's a horizontal translation, 4 to the left. Now that gets us the image point, x comma y, is going to become x minus 4 comma y minus 9. Okay, so there's our mapping notation. Now, let's apply this to the actual point. Okay, so we're going to have the point -1, 8 is going to become, well, it was x coordinate minus 4, so this is going to become -5. And then the y coordinate, which is now 8 minus 9, will give you -1. And so there's the image point of the original point that we were given.
The point 6, -3 is on the graph of y minus 3 equals f of x plus 2. What are the coordinates of the corresponding point on the graph of y equals f of x?
Okay, this is a sneaky question. Okay, this is a really sneaky question. If you are not reading carefully, this question will get you every time. Okay, because notice that what it says here, it says the point 6, -3 is on the graph of the transform function. It is on this graph, okay? And we want to know what the corresponding graph is, the corresponding point is on the original function. Now let's compare these two. What transformations have occurred? Well, to get the y by itself, I'd have to add 3. So that means a vertical translation, 3 up. To get the x by itself, I'd have to subtract 2, so that's a horizontal translation, 2 to the left. Now, that means this is my image point. I'm going to have x comma y is going to become x minus 2, okay, comma, y plus 3. Now, the point that I'm given, this 6, -3, is on this graph, and this is what's different here. Normally, you'd be given this point and asked what its image is, but here, you're actually being told what the image is and being asked to go backwards to get the original. Well, now let's take a quick look at this. If 6 is equal to x minus 2, and let's maybe do it over here, 6 is equal to x minus 2, bring that over, that means 8 was equal to x. If -3 is equal to y plus 3, y is equal to -6. So the original point was this point 8 comma -6. Okay, that is the answer that they're looking for. Okay, again, it becomes really, really difficult. Okay, a lot of times when people read this, the very first thing they do is they put this point in and they transform it. But you got to read this carefully to realize that no, this point is the transformed point. I want to go and undo what that function did to it.
If f of x equals x squared minus 3, then describe how the translation y minus 2 equals f of x minus 4 will affect the domain and range of the function.
Okay, well, to know how a set of transformations will affect the domain and range of a function, and by the way, this is a really good question. This is an exam type question for sure. In order to figure out how that works here, I need to know what the domain and range are for the original. Now, fortunately, this is just a simple quadratic, so I know that the domain will be all reals. The range, well, I got to look at this. If I drop the -3 here, I know that the range, I should say, because that's what we're talking about, the range, will be greater than or equal to 0. This translates that 3 units down. So instead of being greater than or equal to 0, this is now greater than or equal to -3. Okay, now let's take a look at the transformations here. Okay, and I'll do this specifically with the image point. What is this? Well, this is a vertical translation 2 up, because I would take that 2 and add it to both sides here. So this is going to be y plus 2. This is a horizontal translation 4 to the right, because to get x by itself I would add 4, so x plus 4. So this is what my point is going to look like here. Now, think about what this is going to do to my graph here. If I translate the entire parabola 4 to the right, nothing changes. Okay, it was an infinite domain anyway, so nothing's going to change. So my new domain here is still going to be x is an element of the reals. My range, however, will get affected, because my range originally was greater than or equal to -3, and now I'm going to move that 2 up. Well, what's 2 up from -3? -1. So y is greater than or equal to -1. Okay. So in many ways, when you're looking at these transformations here, it's often more important to identify what doesn't get affected. Okay, a horizontal transformation does not affect the range, just like a vertical translation does not affect the domain. Okay, but for example, the horizontal translation here still didn't affect the domain, and so you gotta kind of think these things through carefully.
The graph of f of x equals x plus 2 squared minus 4 is translated 2 units to the right and 3 units down to obtain the graph of y equals g of x. What is the equation of g of x?
Okay, this question here is putting transformations into a graph that's been transformed. Okay, and I used to do this a really awkward algebraic way, but there's a pretty straightforward way of doing this. Notice that the function that we have here is a quadratic. So let's do this. Let's compare the original, okay, y equals x squared, to the transform graph that I've got here, y equals, this is going to be f of x plus 2 minus 4. So y equals x plus 2 squared minus 4. Now, what we've done here, to get x by itself, I'd have to subtract 2. So this is a horizontal translation 2 to the left. And to get the y by itself, I must have subtracted 4. So this is a vertical translation. Oops. Sorry, I was going to write 2. I mean 4 down. Okay. Now, that's how this function compares to the original. Now look what we're doing here. We are now going to translate this. We're going to make this a horizontal translation, 2 to the right, and then a vertical translation, 3 down. Now let's think about this. What does this mean then? So therefore our total, okay, look at what's going on here. I'm combining 2 to the left and 2 to the right. Well, okay, if I go 2 to the left to start off with and then 2 to the right, well, that means there was no horizontal translation. It didn't move horizontally. I did move, but I moved it right back. Now, this is 4 down, and I'm going to translate it an additional 3 down. So that means vertical translation, 7 down. Okay, so what does it look like? What does a parabola look like that has had no horizontal translation and 7 down? It looks like that. Y equals x squared minus 7.
A function f of x has a domain represented by x such that -5 is less than x is less than 4, where x is an element of the reals, and a range represented by y such that 0 is less than or equal to y is less than or equal to 10, where y is an element of the reals. What is the domain and range of the image after the translations y plus 4 is equal to f of x minus 6 have been applied?
All right, well, a question like this is most easily answered by just looking at what the transformations are, specifically getting the image point here. Notice that to get the y by itself, I'd have to subtract 4, so this is a vertical translation, 4 down. And then to get the x by itself, I'd have to add 6. So that would be a horizontal translation, 6 to the right. And that means my image point would look like this. X plus 6, y minus 4. Now, I know that this translation right here, 6 to the right, will not affect the range, but it will affect the domain. So my new domain is going to be a set of x values such that, now what I'm going to do is I'm just going to add 6 to the endpoints of my domain here. So negative 5 and 6 is 1, 4 and 6 is 10, where x is an element of the reals. My range will not be affected by that horizontal translation, but it will be affected by the vertical translation. So I'm going to take the endpoints of my domain and apply this translation to it. I'm going to move those 4 down. So 0 minus 4 is negative 4. 10 minus 4 is 6. And that's really all you got to do.
As the result of a transformation, the graph of y equals x cubed becomes the graph of y minus 4 equals x minus 3 cubed. The point 3, 27 becomes the point 6, y. What is the value of y?
Okay, well, there's a couple of ways to do this question right here. First of all is to take a quick look at the image point. So you get x, y. And if we take a look at our transformations here, this is, remember, what do I got to do to get y by itself? I have to add 4, so it's going to be 4 up. So this will be 4 up. And then to get x by itself, I'd have to add 3, so it's going to be 3 to the right, which is x plus 3. Then what we could do here is we could take our original point here, 327. Okay, 3 plus 3, okay, is going to be 6. 27 plus 4 will be 31. Now, that's one way of doing this, or we can simply recognize that we actually have the entire function right here. In this particular case here, this question might have been better if we didn't actually tell you that it was x cubed, because all I really have to do in this case is plug in that the x coordinate that I've been given right here and solve for y. So that's going to be 6 minus 3 cubed. Okay, well, 6 minus 3 is 3, cubed is 27, add 4, 31. So either way you want to look at it, you're going to get 31 as the answer for y.
Complete the following table.
So this question here is really just asking us to think about all the different ways that we've been shown how these transformations can be communicated. So in one case here, for example, we're given the original point here, negative 1, 6, and I'm asked to translate it 2 to the left, 4 down. Well, let's just think about this. What is 2 to the left of negative 1? Okay, well, 2 to the left of negative 1 is negative 1 minus 2, or negative 3. Okay, and then I've got 6 here, and I want 4 down. So 6 minus 4 is 2. So there's your image point. So this is one way of doing it, just describing the transformation. Another way of doing it is to kind of dance around that by saying, okay, I'm going to replace y with y minus 2. Now that's in the function. So now I've got y minus 2 is equal to f of x. So what transformation is that? Well, to get the y by itself, I'd have to add 2 to the other side. That's a vertical translation 2 up. Okay, vertical translation 2 up. And this means I just take the y coordinate and add 2. So negative 2 plus 2 is 0. So this becomes the point 3, 0. Or I take a quick look at the transformations in function notation. Okay, and we're going to come up with the image point. Well, to get the x by itself, I'd have to add 5 eventually. So that's my transformation, 5 to the right. And notice that the y is already isolated. And what I did was I added 4, so this will be y plus 4. And actually, because they gave me the original point as xy, that is the thing that I'm looking for here. This is the answer. X plus 5, comma, y plus 4. Now this last question, this is an interesting one because we're given the image point and I'm asked to go backwards. Now notice what this is saying. It says translated 6 to the right. Okay, so 6 to the right would look like this, x plus 6, and 3 up would look like this. Now that is coming at it from our original point. So So this is how this works here. Negative 7 has to be x plus 6. Well, subtract the 6 and I get negative 13 is equal to x. Negative 4 is equal to my y plus 3. Whoops. So bring that 3 over, subtract it, and I'll get negative 7 is equal to y. Now, in this image point right here, remember, these are the original x and xy coordinates here. So what I've just found here are the originals, and the point was negative 3 comma negative 7. So over here, I would write negative 13. Sorry, I said negative 3 a couple seconds ago. I meant negative 13, negative 7. That's what we're looking for.
Determine an equation in the form y minus k is equal to f of x minus h, given the following graph of y equals f of x and its transformation.
Okay, well, for this one right here, the trick is just to realize what's the original graph, what's the transformed one. And the dotted one here is the original, this one is the transformed one. What I'm going to do is the transformations that have occurred here have just been translations. Okay, that's it. So notice that this thing has been moved, and the easiest way to do this is to compare the vertices. Notice it's been moved 6 to the right, so a horizontal translation 6 to the right, and then it was on 0, it's been moved down, and it was moved 7 down, so a vertical translation 7 down. Now think about how that has to play out inside my function here. If I want 7 down, okay, that means I need to be subtracting 7 to isolate the y here. So that must mean I'm adding 7 here right now. So this is y plus 7 equals. Now just think about that. To get that y by itself, I would subtract 7. That's what this is saying. Good. F of, 6 to the right, means that if I'm isolating the x, I have to add 6. So if I'm adding 6 to get the x by itself, then this must have x minus 6 in it. And that's the equation that I'm looking for.